We have refreshments in back that you're welcome to enjoy. We'll start with the public portion of Dan's defense. He'll make a presentation that lasts for an hour on his dissertation. You're welcome to ask questions during his presentation. We'll also reserve some time at the end for final questions. Following his public presentation will be the private portion of his defense. It'll be in a different room with Dan and just his committee members, which are Alon Efrat, Mike Sanderson, Stephen Kubarov, and myself, John Casesioglu. So Dan will present on his dissertation, which is parameter advising for multiple sequence alignment.
Great. Thanks everybody for coming this afternoon, morning, and for going to listen to my talk. So my dissertation research has been on parameter advising for multiple sequence alignment. So I'd like to start by quickly reviewing what exactly I mean when I'm talking about multiple sequence alignment. So the sequence alignment problem, we're given a set of unaligned sequences. So these sequences can be strings from, say, English language, or DNA sequences over the DNA alphabet, or in our case, we're going to be concentrating on proteins. So these strings are over the 20-letter amino acid alphabet. So given these unaligned sequences, and an objective function, which gives you a score for, say, aligning one amino acid with another or adding a gap to the alignment, what we're trying to find is an m by n matrix. So this is a grid where each row represents one sequence from the set. So this represents that sequence with inserted gap characters, so little dashes here. And while there's many alignments that satisfy this first condition, we want to find the one that's optimal under the objective function. So we're trying to find the best alignment of the M sequences. And any one of these programs that does this, we're going to refer to as an aligner. So an aligner is any tool that takes unaligned sequences, outputs an alignment. So the multiple sequence alignment problem is sort of fundamental in biology. So whether you're doing homology search or structure prediction or phylogenetic reconstruction, all of these problems all start with a multiple sequence alignment of the sequences. But all of the standard formulations for multiple sequence alignment are NP-complete, which means that as we grow the input size, you're probably not going to find an optimal solution in a realistic amount of time. So because of the importance of the problem that we need a solution for and the difficulty, there's many popular aligners out there that are going to find close to optimal alignments. One of the issues that comes up is that each one of these alignment tools has lots of parameters that if you change the parameter settings, you get a very different result. So most people pick their favorite aligner and they go and they use whatever default parameter choices are given. So these parameter choices are given for all inputs, and they're made to be good on average. So these parameter choices give the best accuracy across all the possible inputs that you're going to see. And we can find the optimal default parameter choices using inverse alignment. So that was shown by John and Igu back in 2007. But these default parameter settings, even though they're best on average, might provide a poor alignment for some inputs. So this is an example of two alignments of the same set of sequences here. We actually know what the correct alignment is supposed to be. So this red region is supposed to be aligned together, but under the default parameter settings, it's sort of all over the place and not aligned correctly. But under an alternate parameter choice, we do align this set of sequences correctly. So the question I'm trying to answer with my dissertation has been, how can we find the parameter choice that's best for a given input? So make an input-specific choice of the settings for all of the parameter values for an aligner. And to do this, we came up with a method that we call parameter advising. So advising takes unaligned input sequences here, just like an aligner would, and it has a set of parameter choices. So these choices are exact values to all of the tunable parameters for an aligner. So given this set, we run the aligner once for each one of these parameter choices to produce a collection of alternate alignments of the same set of sequences. And then once we have this collection of alignments of the same set of sequences, we're going to estimate their accuracy. So normally accuracy of a multiple sequence alignment is measured with respect to some reference. And if that reference is known, then we don't actually have to do sequence alignment. So in practice, we don't have that reference. So we're left to estimate the accuracy. So one of the problems that we're going to try and solve is finding a good estimator for accuracy. Once we have the collection of alignments that's labeled with this estimated accuracy, the advisor is going to choose the one with the highest estimated accuracy from this set and return that to the user. So what we're trying to do in essence is find the parameter choice from the set here that gives us the highest estimated accuracy alignment for the input. For a user though, at the outset, it looks just like any other aligner, where you input unaligned sequences and you get some aligned set of sequences as output. So to sort of give an overview of what I'm going to talk about today, I'm going to start by talking about our parameter advisor and exactly how we find the new accuracy estimator that we came up with that's called Facet, so the feature-based accuracy estimator that we published a couple years ago. I'm going to talk a little bit about the fact that finding the best advisor, so that is the best accuracy estimator and the set of parameter choices to use together, is actually very hard. It's NP complete, so we're not going to be able to do that in practice. So we have an approximation algorithm to find a very good advisor set for an accuracy estimator. Once we have a parameter advisor, we can sort of expand that in two ways. The first is by applying our advisor as an aligner advisor, so choosing not just the set of parameter choices to use, but the aligner itself. So you could get alignments from different aligners and pick the one that you think is best, rather than just using a single alignment tool. And we can expand that in a different way by looking at the protein sequences themselves. So proteins don't necessarily have the same mutation rate along their length. So we can exploit this difference in mutation rate to choose different parameter settings at different locations that might give a better global alignment of the sequences. And then finally, I'm going to talk a little bit about our most recent work on improving the accuracy estimator by looking at core columns of an alignment. So core columns are highly reliable regions of a benchmark, but we don't actually know where they are in a computed alignment. So we're going to have to try and infer the location of these highly reliable columns to improve our accuracy estimator. So coming back to this picture that we've seen before, I'm going to start by looking at the parameter advisor itself. And the parameter advisor has these two components. One, like I mentioned, is the accuracy estimator. So that's going to be our estimator called Facet. And then the other is the set of parameter choices that we want to use. So I'm going to start by talking about the estimator. And then it turns out we can find a set that works well if we already know what the estimator is. So just to sort of catch everybody up on how I mentioned that accuracy is normally measured with respect to some reference alignment. So if this is the reference alignment here is on the left, so this is the ground truth. This is what we're going to know is correct. And on the right is some computed alignment over the same set of sequences. We measure accuracy as the fraction of substitutions from the reference alignment that are recovered in the computed alignment. So in this case, the substitution ER is recovered in the computed alignment, so that one is correct, where the substitution RH is not recovered correctly. So it's misaligned in our computed alignment. Same thing with this, the substitution EH is also misaligned here. And I say substitution, but it can also be the same character. So we still, in our world, we still call that a substitution here. And we do this on core columns of the reference. So these reference alignments are created by looking at the 3D structure of proteins and how they fold in 3D space. And these core columns are points where the alignment of the 3D proteins are very close in location in 3D space. So these are labeled in our reference alignments, and we know these to be highly reliable. So we only measure accuracy here. So for these two columns in red that are the core columns, we get 66% accuracy for this example because 4 of the 6 substitutions from the reference alignment are recovered correctly. So without such a reference alignment, right, we don't usually have these in practice. What we're left to do is estimate the accuracy. So we came up with a method that we call Facet. So I mentioned before, it's the feature-based accuracy estimator. And we're going to estimate the accuracy of an alignment as a polynomial on feature functions. So these feature functions are easily computable features of an alignment. So they're things that we can actually measure without rough reference alignment. And they trend with true accuracy. We can also efficiently find the polynomial coefficients, so we can learn the weights for these feature functions when we sum them together. And the feature functions that we've developed are novel and efficient to calculate. So I'm going to review all of these in turn. So I mentioned that our accuracy estimator facet is, so here I'm going to represent it as a sum, is a polynomial in the feature functions. So the feature functions that we use, f sub I of a, are the features of an alignment A, and they give a real value. So this is a number between 0 and 1. And the most simple estimator is going to be a sum of these values. So a weighted sum where the coefficient of the feature I is weighted for each alignment. And that gives you a real value for our accuracy estimate. A more complicated estimator would be, say, a quadratic, where you're summing not just the feature functions themselves, but products of pairs of feature functions. It turns out we don't actually have to consider high-order polynomials because we can, because these features are real values, we can condense them down into just learning coefficients for a linear estimator. So we're going to learn the coefficients once we have the features. We're going to learn the coefficients using a set of examples. So each one of these examples has an alignment itself, and then we're going to use alignments of benchmarks where we know the ground truth. So it has an associated true accuracy. We can actually measure that because we know what the ground truth is supposed to be.
Yeah.
Yes.
So good question. You lost me on the last slide where
Yeah.
you said you don't need to do higher order features. Can
Yeah.
you explain that with a little bit more?
Yeah, yeah.
Because if they don't span the same space.
Right. So it's an issue of, so the feature functions are real values of an alignment. So we can come up with just a new feature, say, that's this product here, right? So we would expand the number of features that we have, but the new features that we create would be products of the real numbers of existing features.
Okay, but you're still enriching the basis set.
You're still enriching the number of features that you have, but then we can reduce it to just learning a linear number of coefficients. Right, so we're going to learn from examples where we know the ground truth and we can actually measure the true accuracy. So we can either fit, when we learn the coefficients, we can either fit the actual values of the estimator to be as close as possible to the true accuracy, or we can use differences in accuracy pairs. So I mentioned earlier when we do parameter advising, you're actually ending up ranking alignments. You're trying to pick the best one. So it doesn't necessarily matter that we get the accuracy estimated correctly, as long as we're ranking the alignments correctly and picking the one with the best true accuracy. And in either of these cases, we're going to learn the coefficients using either a linear or a quadratic program. So I've been talking this whole time about learning the coefficients, but what are the underlying features? What are these things that we're going to be using? So the features that we use are fast to evaluate, so we don't want to increase the overhead on the multiple sequence alignment process. So these have to be quick to figure out a number for each alignment. And we want to measure novel properties of a multiple sequence alignment. So things that might not be currently used to figure out alignment quality. And then we want to use non-local information. So we can give a long range of information to sort of sum what's happening in an alignment, rather than using just a column-specific score in the alignment. And then a lot of them, because we're using proteins, can involve secondary structure. So I'll discuss a little bit what secondary structure is, but proteins have this special feature where they fold into things, and we can exploit that to sort of see how well we do with the multiple sequence alignment. So some of the features, just sort of to give an example, the ones that don't use secondary structure are things like amino acid identity. So this is just the normalized count of how many substitutions are of the same amino acid class, so the same letter. Or average substitution score, so this is the sum the normalized sum of, say, the Blossom 62 matrix scores for the replacements that are in an alignment, or information content, which is sort of the difference in amino acid distributions in a column versus some known background distribution of amino acids being represented. And there's quite a few others that don't use secondary structure that all tend to correlate well with true accuracy. But because, like I mentioned before, we're using proteins, proteins have secondary structure, so we're going to use a very naive model of secondary structure, which labels each amino acid in the alignment with one of three classes. So the first is something like this, an alpha helix, and they're labeled, say, in a multiple sequence alignment in blue. A beta strand here is labeled, it's yellow in the picture, but it's green in the alignment down here, and then coil. So coil is just sort of anything else, any other type of structure that's in the alignment. So given that we can predict secondary structure for a multiple sequence alignment, we can come up with a bunch of other features that sort of use this to tell us more things about an alignment. So the first is secondary structure percent identity. So this is similar to amino acid identity, but it's over the three-letter alphabet of secondary structure classes rather than amino acids. Secondary structure agreement sort of is like identity, but it gives a little bit of a wider window of information to see if they agree in secondary structure class. And then secondary structure blockiness is actually the most informative feature that we came up with, and it's actually quite interesting, so I'm going to go into that in detail, but there's a few other secondary structure features that we consider. In total, there's 12 features that we consider for facet, and when we learn the coefficients, about 6 of them end up getting used at any point. So secondary structure blockiness actually came from a little bit of intuition of just staring at alignments that are labeled with secondary structure over and over again. But you can see that really high quality alignments, high accuracy alignments tend to have secondary structure that's sort of grouped together into what I'm going to refer to as blocks. So a block in an alignment is an interval of at least L columns. So these are columns that are all right next to each other, and a subset of at least K rows. So the order of the sequences in a multiple sequence alignment are not necessarily, they're arbitrary. So it doesn't matter that these are a disjoint subset of rows. And then we want this block to have the same secondary structure. So an interval of rows, a subset of columns, an interval of columns, a subset of rows that share the same secondary structure legally. And so this is one block in the alignment. We can see it satisfies all those properties, and we can sort of find all of the blocks all over, right? So these are all of the blocks that satisfy what I've said before. And what we want to find is a packing. So a packing for an alignment is a set of blocks from the alignment. So a subset of all of the blocks that we could possibly create that are column disjoint. So none of these blocks ever share the same column, but they all can exist on the alignment. And the value, did you have a question? Yeah.
Can they share? You said that you are only picking K of the alignment.
Yeah.
Can they share the ones that are not picked to participate in the block? Or the block always involved all the rows?
Yeah, so the block they have to be column disjoint. So like, there could be a green block here, but we can either pick the green block or the blue one, right? So where no two blocks can occupy the same column no matter how it works. And then the value of a packing is just the number of substitutions that are contained in blocks that we pick for the packing, right? And then the blockiness feature, so what we're going to end up using is the maximum value of any packing that we can put on the alignment. So even though it looks like a bin packing problem, which is not an easy thing to compute, we can actually find an algorithm that runs in O of mn time using by solving a longest path problem on the alignments. And the details are in the paper. I don't have time to go into it now, but basically each column becomes a node in the alignment, and you can find the longest path. So now we have all of the feature values, and we can create our accuracy estimator. So on the left here shows the plots of some of the features that we use. Oh, yeah, sorry.
Sorry to interrupt again. maybe you explained this before and I missed it. Are the rows given like a fixed ordering?
No, so the ordering of the rows is arbitrary. So that's why it's a subset of rows and not a...
But your packing is dependent on the order that you picked, right? Because the
packing is not dependent on the order of the rows at all.
Okay.
It's dependent on the columns being disjoint, not the rows.
Dan, can you flip one
Yeah,
slide
sorry,
back?
it's
So,
okay.
just slide back,
Yeah.
wherever you had the big black blocks.
Yeah.
Yeah.
There we go,
So, the two blue things, they're really one block.
It's really one block. Yeah, sorry. I guess that was where it was sticking. Yeah. Yeah, so this is one block, this is one block. Even though they're separated in space, the order is arbitrary. Yeah. Okay. Good. So this is sort of what the features look like. Each one of these dots in these plots is a computed alignment of a benchmark. So we actually know what the real alignment looks like, so we can calculate the true accuracy of the example on the horizontal axis, and we can get the feature value, because it's an alignment, on the vertical. And then each one of these alignments was computed. So we can see here, this is blockiness, secondary structure identity, and structure agreement. But when we use a linear combination of them to create facet, it has much less spread and is very tight. So that's sort of what we need to have for our accuracy estimator to be able to choose between alignments. Having too much noise will give us a really bad choice. Bless you. And when you compare facet to other estimators, so facet is here on the right, and the colors look a little bit messy, but this is pred-SP in the middle and MOS on the left, and each one of these is the same plot that I showed before, where true accuracy is plotted on the horizontal axis, and the estimator value is on the vertical. And what we need for parameter advising is to have an estimator that has very high slope, but low spread. So we can see MOS has very high slope, but has a lot of spread. There's a lot of noise in the estimator, where pred-SP has very little spread, but you're really going to have a hard time distinguishing between two alignments because the slope is so low. And MOS sort of has the middle ground between the two. And it turns out that for parameter advising, our estimator happens to work the best to distinguish between alignments. So now we have our accuracy estimator, and that's one of the two parts of a parameter advisor. So we have the estimator. The question that we have to solve now is, given the accuracy estimator, how do we find the optimal set of parameter choices that's going to work best for advising? So I'm going to walk through a little bit of an example of what the problem is of finding an accuracy estimator an advisor set given an accuracy estimator here. So we have a set of benchmarks which are sets of sequences where we know the ground truth, and we can measure the true accuracy of any realignment of those. And we have a universe of parameter settings, and this is sort of all of the possible sets of values that you can give to an aligner. So when you use a parameter choice, say the green parameter choice, to align the triangle benchmark, right, we get a computed alignment. Because we know the ground truth, we know its true accuracy on the vertical here, and we know its estimator value on the horizontal. And we can realign each of the benchmarks in our set of benchmarks to get real values for real computed alignments under the parameter setting within our universe. And we could do that for all of the parameter choices in our universe here to get a set of alignments over benchmarks where we know the true accuracy and we know the estimator value. And the lines here don't actually mean anything, they're just to connect visually alignments of the same benchmark. So if we want to pick one parameter choice to use, that problem is pretty easy. So we look at, say, the average accuracy of the green parameter choice is the average accuracy of all of the alignments that are created. So the accuracy of the circle here is right about there. Same thing with the diamond and the triangle. So the average accuracy for this parameter choice over our set of benchmarks is right here. It's the average value along this axis of all of the alignments that are created for that parameter choice green here. And we can do that for all of the parameter choices in our universe. And we can say that the blue parameter choice gives the best average accuracy over all of our benchmarks. And that's the default parameter choice that we should use, right? It's best on average. And that's our optimal set of cardinality, say K1, right? Which is also the default. The problem gets a lot harder when you try and consider a set of 2 parameter choices that we're going to put into the advisor. How do we pick a subset of our universe that's of size 2 that gives the highest average accuracy over our benchmarks? And the way we're going to do that is we're just going to we can run the aligner, the advisor, for all of the subsets of size 2 from our universe. So say we use just the green and the red parameter choices in our advisor, we're left with just these alignments here, and the advisor always picks the alignment with the highest estimator value, so the furthest one to the right, and then you get back an alignment with the accuracy that corresponds on the vertical axis. So the average accuracy of these 3 choices, so the advisor here chooses the red triangle because it has higher estimated accuracy, it's further to the right, and we get the accuracy here. So the average accuracy of the alignments that the advisor chooses is right about here on the axis, right? And then we can do that for, say, green and blue. And here is an example of where noise in the estimator actually gives us the wrong choice. So the advisor is going to choose the blue circle here because it has higher estimator value. It's further to the right. But the optimal choice is actually the green circle here, right? It has highest real accuracy. But the advisor doesn't actually know that. An oracle advisor would. So an oracle is like an all-knowing being, right? And it knows the true accuracy of all of these alignments. And we're going to use this as sort of a theoretical upper bound. An oracle can't actually exist without knowing the ground truth alignments for each one of these benchmarks. And we can do that again for blue and red. And we can see that for a subset of 2, using green and red would be our best possible choice because it gives us the best advisor accuracy on average across all of the benchmarks. So I mentioned before, so parameter choices just to sort of make sure we're,
Back in the how much does this depend on whether or not your benchmarks are representative of what you're going to see in the future?
Yeah, so that's a really good question. It's you sort of hope that it is. You can only do as good as things you've ever seen. When I get to the results, I'll show that the benchmarks that we actually have over-represent really easy things. So we end up having to weight hard things because we assume in general you're going to see things sort of across the spread of difficulty. But it's really easy to make an easy-to-align benchmark because they're all really similar. But it takes a lot more work in the wet lab to get an example of something that's not very similar. Does that make sense? So we will correct for that. Yeah. So just a quick sort of forcing in what a parameter choice is. So we're going to focus on the Opal aligner that was developed in our lab here at the U of A. And a parameter choice is, as I mentioned before, it's a setting of all of the values, setting for values for all of the tunable parameters for the aligner. So here it's a 5-tuple where sigma represents the replacement matrix. So this is something like BLOSSOM or PAM or VCML, which tells you what it costs to replace one amino acid letter with another. And then the other 4 are gap insertion and extension penalties. So how much does it cost to insert a gap? How much does it cost to extend a gap? And so a parameter choice is a value for all 5 of these choices. And then our universe is sort of all of the possible sets of these settings. We actually have to come up with a finite set so that we can run our algorithm, but you could imagine sort of going as detailed as you want to and increasing the size of the universe. So the advisor set problem takes as input, just sort of trying to sort of say this very well, is the cardinality bound K. So the larger the size of the advisor set, the more times you have to run the aligner. So the higher the overhead of running parameter advising. So we want to keep the size of the advisor set small while still increasing the accuracy of the output alignment. So we can specify exactly how many parameter choices we want to choose. We want to take in the universe of parameters that we could have. So for a specific aligner, we have some finite set of the universe. And then we're going to learn from a collection of examples, which are realignments of benchmarks. So because these are alignments of benchmarks, we know the true accuracy, and then we know the estimated value. And then, like Todd pointed out, we might have an overabundance of really easy benchmarks. So each of these benchmarks has a weight. So we correct for this overabundance of easy benchmarks. And what we're going to find is a subset of the universe P that's no bigger than K, it can actually be smaller, that maximizes this objective function here, where we're summing over all of the benchmarks, the value of the accuracy of the advisor's choice for the parameter set P. So for a set of parameter choices, we're going to get a collection of alignments of benchmark I, and then the advisor is going to choose the alignment with the highest estimator value. Because we know the ground truth alignment, we can actually get its true accuracy, and that's what's output here. So the true accuracy of the advisor's choice. And then that's weighted somehow to correct for a bias. It turns out that advisor sets is NP complete. So once again, we're probably not going to find an optimal solution in a realistic amount of time. And that's a reduction from the dominating sets problem. So it turns out that it is polynomial time solvable for a fixed k. So for a very small set of sizes, we can just enumerate all of the possible subsets. And in practice, it turns out we can actually find oracle sets. So again, an oracle is an advisor that knows true accuracy. So if we know the true accuracy is equal to the estimator value, we can actually find oracle sets in practice using integer linear programming for even very large k. So we're going to use these last two properties to come up with a new method that's actually greedy in finding a set for our estimator. So so our greedy method takes an optimal set of size L, right? So some optimal set that we can find in polynomial time for a very small size, and greedily adds a parameter from our universe that gives us the best advising accuracy with that set. Once it finds that, it then finds another set from our universe that we haven't already used and keeps building and building until we get to a set of size k. So given an optimal set of size L, it turns out that that greedy approach is an L over K approximation algorithm. So that means the greedy solution is never going to have an advising accuracy that's less than L over K times the advising accuracy of the optimal solution. So say we're given an optimal solution of size 5, and we want to find a greedy solution of size 10, we can guarantee that the advising accuracy of our greedy solution is never more than, or never less than half the optimal advising accuracy. And it turns out that that approximation ratio is tight. So we can find an example that hits L over K exactly. So now we have a way to find our set, and we have our accuracy estimator that I showed before. So we're going to evaluate the accuracy of advising by looking at facet as well as comparing it to other estimators for parameter advising, looking at 800 benchmarks where we know the ground truth alignment, and evaluating using k-fold cross-validation to make sure we're not training on something that we're then testing on. So this is a plot that we're going to see quite a bit the rest of the morning. So along the horizontal axis here is the cardinality of the advisor set. So like I mentioned, the more and more parameter choices you have in your advisor set, the more times you have to run the aligner. So the slower it's going to be, but hopefully the better accuracy you're going to get from the advisor. The vertical axis is the average advising accuracy over all of the benchmarks that we looked at, so over the 800 benchmarks that we considered. So this plot shows the advising accuracy using facet on greedy sets of increasing cardinality. And we can see as we increase the cardinality, we do keep increasing the accuracy, but it starts to plateau eventually. So this direction is better average accuracy. And then we can compare that to using other accuracy estimators. So TCS is sort of another accuracy estimator from the literature, and it's actually the next best that we found in practice. And we can see that Facet actually does quite a bit better, and then these two others that we also have from the literature. So for parameter advising at least, Facet has the highest advisor accuracy.
Why is the accuracy start from 0.5?
Yeah. So that's sort of to Todd's point. I forgot to mention that. So we weight the benchmarks in the benchmark suites that we have, and I'll show it on the next slide. Actually, there's an overabundance of benchmarks that have really high accuracy even under the default parameter setting. So what my work is trying to do is trying to improve the accuracy of the ones that can't be aligned easily. So we weight these bins together, and because of the way we're doing the weighting, the default parameter choice has an accuracy that's just above 50%. So I'll get to that in just a second, but yeah.
I have a different question.
Yeah.
You say it does much better.
Yes.
The graph goes from 0.50 to 0.56, but the limit is 1.0.
Yes, the
Right.
limit is
So-
1.0.
Why is that much better, going from
Yeah.
0.53 to 0.55?
Right. So again, it's because of the weighting we're doing. We're emphasizing these lower, and yeah. So the next slide is literally talking about that point. So this shows all of the 800 benchmarks that we used. It's a little over 860, and how many end up having. We binned the benchmarks by their accuracy under the default parameter setting. So this is sort of the best average parameter setting. And you can see that 400 of them already have accuracy above 90%. So it's already doing really, really well. What we want to do in this work is say, for these ones down here, where under the default, under the average, we're doing really poorly, right? Like the accuracy is less than 10%. We're getting almost everything wrong. Can we make those better? So we average across the bins. So the default accuracy ends up being near 50%. And that's on purpose. So on these bottom bins, I'm going to skip ahead. Here, so again, advising accuracy is on the vertical axis, benchmark bins are across the bottom. So on these benchmarks where for the default the average accuracy is less than 5%, we're getting an increase in accuracy of about 20% over using just the default. So when you average across the bins, a lot of that gets washed away, right? But on these lower bins where we really can make a difference, we are making a big difference. So it's scaled down. So 4% doesn't look like a lot, but it is actually significant. Right, so explaining the rest of this plot. So the default parameter on average for the average of the, say, 12 benchmarks that are in this bin is in blue. The average accuracy using our advisor on the greedy set is in red. And then this dotted line is the oracle. So again, this is a theoretical upper bound of how well we could possibly do using advising. So the best we could ever do is this, and we're getting pretty close by using advising here. And like I said, on the hardest to align bins, we're getting almost 20% increase in accuracy over using just the default parameter setting. So now we've proven that parameter advising is a thing, and it works really well. How can we extend parameter advising to other applications? Yeah. Yes.
The very last, the 100% bin over there, the greedy algorithm is a touch below the default. Is there a significance to that?
Is there a statistical significance? No, not that we found. So I don't have all of the stats in front of me, but I don't think that was statistically significant. Because you're already getting alignments that are really, really close to perfect, so it's just sort of like a little bit of noise in the aligner.
Why is it slightly worse on the last bin?
Yeah, that's a good question. It's really that the default alignments are just so good that just by chance you're getting one or two replacements that are bad. And our accuracy estimator isn't perfect. So it's choosing the one with the highest estimated accuracy, but it might be a little different than true accuracy. Yeah. So it's still really close to the best you could possibly do with an oracle. Right? Does that make sense? Okay. So all of the work that we've done so far has been focused just on the opal aligner that was developed here. So one of the things that we tried to do, and we published this last year, was apply parameter advising to aligner advising. So what aligner advising is doing is choosing the choice of aligner as well as the parameter settings that go into the aligner, and include one or more choices for the tunable parameters for each one of these programs. So we've seen this picture before where we take the unaligned sequences and we go through the process of advising. We're going to change this section right here and push the aligner inside the advisor set, and then our collection of alignments now might come from different alignment tools. Okay. So there's sort of two flavors of ensemble alignment that we come up with. One is default aligner advising, and this uses 17 tools from the literature. So these are popular aligners that everybody sort of uses, and we're going to use just the universe of parameters that we're choosing are just the default parameter settings for each one of these aligners. The other flavor is going to be general aligner advising, and that's the universe of parameters is only 10 of these tools, but for each one of these we dug down and sort of tried to enumerate individual parameter universes for each one of these programs, and then we concatenate them all together to get a much larger universe of parameter settings and alignment choices. So with these two, we also now have a set of parameter universes for individual aligners. So the first thing we wanted to test, so we've already seen that parameter advising does increase accuracy using the opal aligner. We wanted to test for other aligners, does parameter advising still actually work? And we can see, so Mummels is not necessarily a standard aligner, but using Mummels as well as ProbAlign, they were the two next most accurate aligners in the toolbox that we used. We do get an increase in accuracy as you increase the advisor set cardinality, so as we add more and more choices to the set that we use. We do get an increase in accuracy, and they all sort of plateau eventually. When we combine them together into general advising, so this is where the set of parameter choices might include non-default parameter settings for each aligner, we can increase accuracy even more over using any single alignment tool. And then it turns out that using default aligner advising, so just selecting the tool and using its default parameter choices, gets a little bit of a higher accuracy on the testing data. So like I mentioned before, we're doing cross-validation, so we learned on a set of benchmarks and we tested on another set of benchmarks. So it turns out that general aligner advising, even though it gets higher accuracy on training data, doesn't generalize quite as well. But we do get a boost using either ensemble method over using any single aligner tool. So now that we've done that, the other thing we were thinking, there's another application of parameter advising to alignment, and we call that adaptive local realignment. So I mentioned earlier that proteins don't necessarily evolve at the same speed at different places in the alignment. So you might have hypermutable regions of a protein that change a lot over time, and you might have really conserved regions that stay very much the same. When we use alignment tools, we use the same set of alignment parameters, and the parameters sort of model the evolutionary process. So using a single choice of parameters might not be the best, but using different choices along the protein might be a little bit better. So this is an example of an alignment here where we can see, so I've colored it because I know the ground truth, but again, in practice, we don't necessarily know that this core column is supposed to be aligned with itself. But we can see that this section is well aligned, and this section is very well aligned. But the section in the middle, we might be able to do a little bit better. So what we did was we used our accuracy estimation tool Facet to sort of label the columns using windows, and we can say that these columns have really high facet score, these columns have really low facet score. And what we're going to do is to figure out how to chop this region out, we're going to expand these bad columns out until we hit something good or hit something else that's already labeled. And we're going to do the same thing here. And now we have this region that either we don't know how well it did or it was a bad column under our facet objective. And we're going to chop it out. And now we have some subset of the alignment and some subsequence of all of the inputs. And we're going to run that through the same parameter advising process that we've seen before. So input the unaligned sequences here, choose a different parameter choice that has a better accuracy, and then reinsert that into the alignment. And it's chopped off a little bit here, but you can see we've taken this region out and inserted the realignment of the subset of sequences and increased the accuracy of the whole alignment by increasing the accuracy of that small region. So we can do this in a couple different ways. So we've seen the default parameter choices here before. Again, these are benchmark bins. So these are binned by their alignment accuracy under the default parameter choice for Opal. If we take those default alignments and just simply run local adaptive realignment or local advising, we get an increase in accuracy all along the bins. So we get, especially down here in the bottom, where those alignments weren't necessarily very good to begin with. And we've also seen this blue line before. The blue bars are global advising, so choosing the best global alignment parameter for the input. When we combine the two, so we're now using local adaptive realignment on each of the choices within global advising, we get this red bar, and we can see, especially on these bottom two bins, where we do have a lot of room to improve the accuracy. We get a very large increase in accuracy. Yeah, Carlos. Yeah.
Just I'm trying to understand why this should work. Right? Because is it sort of trying to exploit some like missing optimal substructure here that
Yeah.
that kind of suggests a dynamic programming algorithm, right? Where
Right.
like you're chopping something and redoing it, but that means that in that point the solution wasn't optimal to begin with. Is that sort of what the exploit is? Your predictor is sort of figuring out here's this piece that you missed.
So when we make the alignment of the whole sequences, so the global alignment of all of the sequences, we're using one parameter objective, right? One set of parameter choices for our objective. But because the proteins might be evolving in different ways in different parts of the alignment, that global parameter choice might not be the right fit for a specific region of the alignment, right? So you can say this is getting a little bit too far into it, but if you have a protein where something is exposed and needs to stay exactly the same to be able to hook into something else, right? That region of the alignment is going to be really conserved, but there might be somewhere else where it doesn't really matter what the sequence is, so it might change a lot. But there might be something in there that needs to stay the same within the structure, but not necessarily the sequence. So what we want to do is exploit that difference in evolutionary history to get different parameter choices in different regions. Yes?
But how do you do this local adaptation without having a reference?
Yeah, so instead of using, so that was that first step where we're using our facet estimator on windows.
Okay.
So we're chopping little windows out, getting a facet score, and then sort of using a sum of the window values to get a column score. Right, because we don't know the reference in practice. So we have to sort of guess which regions are correct, which regions are wrong. And we happen to have a tool for that. Yes?
A few slides back, you had the dashed gray oracle upper bound.
Yes, yeah.
Does the same gray dashed upper bound apply here?
It could, but I don't have that data because the way I redid Opal, I don't know where the core columns are to say which alignments are actually correct. So that's something that I need to go back and do to be able to put that curve in here. Yeah.
It does apply for global advising.
It does apply for global advising, and I didn't plot it here because I...
Right. Well, what I was curious was,
Yeah.
do the red bars get close to the theoretical upper bound?
I don't actually know. I don't have that data in front of me. Yeah, I'd have to go back and look. Yeah, but they might be different because the optimal locally adapted realignment might be better than the global best, right? Yeah, so on this bottom, second to bottom bin here, we're increasing accuracy by almost 26%. So we're getting a huge boost in accuracy. And then, so that was using a set of cardinality 10. We might not necessarily want to use that big of a set because it would slow us down a little bit. So increasing cardinality using local adaptive realignment, we do get a plateau here. And global advising also does well, but combining the two methods again, across all of the cardinalities of sets that you use, increases accuracy. So I'm going to quickly go through our last little project. So I said before that the core columns in a reference alignment are these really highly reliable regions, but we don't know where they are in a computed alignment. So we're left to sort of estimate where they are, and we're going to do that so that we can improve the accuracy estimator and try and focus it down on these regions that we think came from core columns of alignment. So again, we're going to use the secondary structure labels here. Green and yellow are these beta strands, alpha helix. And we're going to take an alignment and look at a column. And if we know the ground truth alignment, we can actually get the coreness. So we measure coreness as the fraction of substitutions from the core column of an alignment, just like we measured accuracy before, but the fraction from the column that are recovered, rather than across the whole alignment. And we can see the accuracy here, the coreness is only 0.8. We're going to reduce that down to a point in high dimensional space. And then use sort of a nearest neighbor model. So once we have these high dimensional vectors, we can say, these group together, and we know, for instance, that they are examples where the center column is core. These are examples where we know the center column is not core. And when we get a new point P, we can say its closest neighbor here is a core column example, and then we can get its distance. And then once we get its distance, we're going to transform that distance into a coreness value using these sigmoids that would fit to example data. So we're going to take its distance, go along the horizontal axis here, come up to the blue curve since it was a core example, and then give its predicted coreness as this value right along here. And then quickly to say facet without our predicted coreness and facet with true coreness, so if we actually knew what the coreness value was, are these two bounds, and with our predicted coreness, we're right about in the middle. But we can boost the accuracy of facet using predicted coreness. Finally, I'd like to give a plug for our tools. They're all available online. You can go find them. So to summarize everything, so parameter advising significantly improves accuracy. We can find the coefficients of our estimator using linear programming. We found an L/K approximation algorithm for finding sets. And we can increase accuracy by almost 20% on the really hard benchmarks. We then extended parameter advising to ensemble alignment, where we're choosing not just the aligner parameter choices, but the aligner itself. And we increase accuracy on average by about 9%. And then adaptive local realignment sort of tries to exploit the evolutionary history of these proteins to sort of get different parameter choices in different regions across the protein. And here we get an even bigger increase in accuracy over using just the default parameter setting in general. Just a little bit of future directions. So we'd like to apply this to DNA and RNA so that we can use alignment advising there, as well as use local adaptive realignment for things like whole genome alignment where the evolutionary history is more pronounced. We need to make the generalization of greedy set finding a little bit better. So we saw that the drop in advisor accuracy when I was looking at the advisor sets for ensemble alignment weren't quite as good for default aligner advising as they were for general. The coreness prediction tool is not quite as, it doesn't generalize as well as it should as well. And then I've actually provided a generalized framework for any domain where you have a lot of input parameters and you know some ground truth. So these are things like assembly or read mapping within bioinformatics, but maybe modeling outside of that. So we might be able to apply the advising framework to new domains. So in the couple seconds that I have left, there's a bunch of people I want to thank, in particular John, for 6 years of of advice, as well as my committee, again, for all being here. All the people at Iger who every step of the way have provided some help, especially Penny, who decided to come today, and then Noah Whiteman, who's not here, Jen, Andy. Everybody from John's lab who has listened to many, many, many talks of mine and maybe not understood what's happening. Also, all of the other grad students who have listened to me babble on about my research over the years. Sarah, who came all the way from New York to be here, and then my mom and my brother and my aunt who are here. So with that, I'll take questions. Yeah.
About 20 slides back, you mentioned, in the interest of time, you mentioned 2 properties that you were able to exploit. One was that if you handled the K subsets, that it was solvable, it wasn't NP complete anymore. But the other one was integer linear programming worked for some definite. What is that?
Yeah. So we can actually, we have an integer linear programming way to set up advisor sets. So if we can solve the ILP exactly, we can get the optimal advisor set. But ILP is NP complete. So it just happened that in practice, for the oracle sets, the ILP completed correctly.
So that's not actually a property, it's just
No, it's just it was just a statement, right? Like, we can use oracle sets, so a lot of the results rely on having the oracle set around even for large granularity.
not to be pedantic, but in the past it's always worked. You don't know if problem n+1 is
Right,
going to work.
exactly, yeah. So actually it turns out when we increase the parameter universe, it gets a lot harder. And if we increase it too much, we might not be able to solve it because it's getting to the edge of that now. Carlos?
You mentioned the type approximation of the Gilbert-NL approximation
For set finding, yeah.
Yeah, so that's with no assumption on the relationship between the oracle and the predictor, right?
No assumption between the oracle and the predictor.
So
Yeah, so it's for any accuracy estimator.
So I'm just curious whether you might be able to sort of squeeze some more result out of this. We go to your plots so you had a plot where you're showing us sort of a scatter plot of this way early on with the slopes, right? The large slopes and the small slopes and the different predictors.
Yeah.
There seems to be structure there that the variance increases, the variance, yes.
Yeah.
Right, so for both the Predis B and facet, it seems like there's more variance anytime there's true accuracy.
Right.
And so I just wonder if you can actually exploit something that says, assuming something else about, right, because your tight counter example, right, your lower bound comes from sort of an arbitrary relationship between those. But
so make an assumption about.
There seems to be actual structure in there that you might be able to exploit, just sort of as a comment.
I haven't explored that fully.
Because you see how the variance increases as you go to true accuracy, right?
Yeah, and there is definitely that point, right? Like, especially since we learned the coefficients, again, we weighted learning facet on these ones where we really wanted to focus our attention. So we sort of ignore the stuff over here a little bit. Not ignore, but put less emphasis there. Yeah.
Okay, great. Thanks very much.
Thanks.